Lecture 8 introduces the method of integration by parts, and this method of integration reverses the product rule that we saw in Calculus 1. So in Calculus 1 we had the derivative of f of x times g of x is f times the derivative of g plus g times the derivative of f. And that means that f times g is an antiderivative for the right-hand side here. So that means the integral of f of x times g prime of x dx plus the integral of g of x times f prime of x dx is f of x times g of x. And rearranging that, we get this rule, that the integral of f of x times g prime of x dx is f of x times g of x minus the integral of g of x times f prime of x dx, where the roles of these two functions are switched. Now, quite often we find that this latter integral is easier to calculate than the integral on the left. We can summarize the formula by letting u equal f of x and v equals g of x, and then dv is g prime of x dx and du is f prime of x dx, and we get the integral of u dv is u times v minus the integral of v du. If we have limits of integration, then the integral from a to b of f of x times g prime of x dx is f of b times g of b minus f of a times g of a minus the integral from a to b, same limits, of g of x times f prime of x dx. Let's try an example. Let's try the integral Let's try the integral of x times e to the x dx. Now the trick here, so our integration by parts is that the integral of u dv equals u times v minus the integral of v du. And of course, when we choose the v, we have to calculate dv, we have to calculate v, so dv should be something that we can integrate. And when we choose u, we have to calculate du, we have to differentiate it, so u should in general get simpler with differentiation. Okay, so here I'm going to try letting u equal x, and that's certainly going to get simpler when I differentiate. And I'm going to try dv equals e to the x dx. And you can see here that this lot is dv, and this is u, and so this is the integral of u dv. So I have to calculate v and du, so I have to differentiate u, and I get du is equal to 1 dx, or just dx. And then v is going to be the antiderivative of dv, which is the antiderivative of e to the x, and that's very easy to calculate, that's just e to the x. Okay, now I fill in the details. I have the integral of x times e to the x dx. That's the integral of u times dv, and that should be equal to u times v. So here's u, here's v, it's e to the x, so that's x times e to the x minus the integral of v, which is e to the x, times du here, which is dx. So that's u, that's v, and that's v, and that one there is du. And now see, the integral of e to the x is easy to calculate, so I get that my antiderivative for x times e to the x is x e to the x minus e to the x plus some constant. And I'm done. We'll look at variations of this. We'll look at definite integrals in class. And then the method gets a little more complicated to apply. There's a common trick you can use that isn't obvious. Letting dv equals dx also works, and we'll do that for the integral of the natural log of x dx. Sometimes you have to repeat the process twice. The integral you end up with, the integral of v du, often turns out to be something you have to apply integration by parts to once more. And we'll do some examples like that in class. And lastly, we'll look at recurring integrals. So this involves applying integration by parts more than once, and then the same integral crops up on the right-hand side of your equation again, and you have to use algebra to solve for the initial integral. And this also works for powers of trigonometric functions. The low powers of sine and cosine we can deal with using formulas from trigonometry and substitution. We can use substitution for sine cubed. But then higher powers of sine and cosine, we can actually use integration by parts. And in fact, we can derive these reduction formulae using integration by parts. We can reduce the integral of cosine to the n to an integral of cosine to the n minus 2. And you can continue to reduce the integral by steps of 2 until you get to the integral of cosine, or just cosine to the 0, which is 1, which you can calculate in a finite number of steps. So we'll have a look at those formulas in class, the reduction formulas and the variations of this method.